Okay, so we're going to start the afternoon session of IPTCom. This is the last presentation for the day, and then after that we're going to have the research roundtable. It's my pleasure to welcome Professor Simon Pietro Romano from the University of Naples, Federico II. And,
thanks a lot. So hello everybody. As Gaston was saying, I'm Simon Romano from Italy, from the University of Napoli. And actually, I'm also the co-founder of Miteco, which is a WebRTC-based company. And the things that I'm going to present today are related to this specific part of my research and engineering activity. This is a joint work with my colleagues Alessandro Mirante, Tobia Castaldi, and Lorenzo Miniero. The title of the talk is Jattack. Jattack stands for Janus attack. And I hope that you have an idea of what Janus means. Do you have an idea of that? Some of you, yes, some others, perhaps not. Janus is a WebRTC media server and gateway, and Jattack is a tool that we devised in order to stress test the performance of such a gateway, but actually I will try to give you a flavor of how this tool can be used also for other purposes. Basically, my presentation is organized as follows. I will briefly introduce the motivation behind this work, then I will quickly move to the description of the architecture of the Jattack's framework, and then I will present some testbed that is used in order to assess the performance of the Janus media server, and then I'll draw quickly the conclusions. So basically, as I was anticipating, Jattack stands for either Janus attack or the French Jattack, I attack. And this is a word that we are using in order to identify the things that we're doing related to scalability assessment of our WebRTC-based platform. So basically, we wanted to have a programmable load generator that might be leveraged in order to properly stress test our server-side backend component that, as I was anticipating, is a media server. We needed this for a number of different reasons. First of all, because we wanted to spot out specific issues related to the implementation of our component, and because we wanted to be capable of providing figures and information related to how you can deploy such a component if you need it to manage a high number of connections. Basically, we had already done some work related to scalability assessment, but if you are familiar a bit with this, you know that the client side of such an integrated framework is usually quite complicated, and especially if you are working with WebRTC, you need to properly generate a number of programmatic WebRTC sessions that are actually used in order to stress test your backend. There are a number of tools that can be leveraged in order to arrive at this goal, but actually we found out that such tools usually become your bottleneck. So if you want to stress test the server, you end out by having a complicated situation whereby the client becomes the real bottleneck of your tests. So how did we design this solution? Basically, this is a component-based framework which has a core that implements the main functionality of any WebRTC stack. And then we have a programmable controller that is used in order to properly realize a well-defined testing scenario. And the architecture that we arrived at is sketched in this slide. You see we have the controller on the right side of the slide. We have Janus, that in this case is the target of our scalability assessment tests. We have on the left-hand side a number of Jattack instances, which are, let's say, the components that we use on the client side in order to properly generate a stress testing load towards Janus. In case you need Jattack to generate real media, you can attach to Jattack instances real media sources, and we have the media generator there for that. Yeah. No, we're not using SIP for this. SIP has been used, we're quite familiar with that. It's perfect for SIP stress testing. It's not, it cannot be easily used for WebRTC stress testing, actually. But it's a great tool in any case. And actually, the approach that we are pursuing is quite similar to what CPP does. Basically, just we'll go back to this for a moment. The HTTPS WebSocket lines that you see there are used for orchestration. So basically, the controller is the orchestrator of the architecture, and it sends commands and receives asynchronous notifications from the other components in order to properly manage a testing scenario. So as I was telling you, the controller acts like the brain in the overall architecture. It basically connects to all of the elements that it has to manage, and it implements the server side of a protocol that we defined on purpose, that is the Jattack Protocol. Basically, such a protocol is a JSON-based exchanging of messages. We have Jattack commands, we have Jattack responses, and we also have asynchronous events. Everything is properly formatted by using JSON messages. How does a complete scenario work? So Jattack is the ARM, is the tool that we used in order to stress test the media server. So basically, Jattack needs, first of all, to connect to the controller. If it needs to generate media, it can attach to one or more media sources. In the examples that we have in the paper, the media sources are actually realized by leveraging the GStreamer framework, which is a very simple framework for real-time streaming. And as you know, it actually generates RTP streams, which are not WebRTC streams. So Janus is needed just for the purpose of making, for example, a plain RTP session become a WebRTC-enabled session. And in that case, it acts as a WebRTC gateway. So it makes a translation between the RTP word and the WebRTC word. The Jattack instances can then contact the backend Janus instances and start negotiating with them by means of commands that the controller is issuing. They can start negotiating WebRTC session and in the end exchanging WebRTC data. Just to give you an idea of the commands, we can add and remove media sources. We can create and destroy sessions. A session is basically associated with a peer connection in WebRTC vocabulary. We can also generate STP offers and answers in order to properly carry out the offer-answer phase. We can handle them. We can receive, let's say, send information related to when we want a session to terminate, or we can issue commands in order to get statistics and detailed information about what's going on inside one or more sessions. As to the events, we have the list that is shown in this slide, basically all of the events that are associated with the creation, so the setup and the proper conduction of a WebRTC session are there. You can recognize, for example, all the things associated with the ICE state machine. Okay, in the paper we presented a detailed campaign where we stress tested a Janus media server. The idea is that Janus is one of the media servers or WebRTC components that can be evaluated by leveraging Jattack, but what is clear is that Jattack has been specifically conceived at the outset by having in mind Janus as the backend. So if you want to use it with other backends, you need to properly fine-tune the part that is related to how the controller interacts with this new media server instance. As key performance indicator, we took CPU and memory load. We did not want the network to become a potential bottleneck. And this was just because we wanted to assess the scalability of the component themselves, meaning both the server side, which is the media server, and the client side, which is our own stress testing tool. We did not want to come out with situations whereby the real bottleneck resides in the communication, so in the network. As far as the estimation of the quality of the sessions that you are going to instantiate, we used the getState command I was telling you before in order to gather statistical information about NACs, so not acknowledgement packets related to the sessions. NACs can be quite easily associated with a good estimation of the real perceived quality of your connection, because it allows you to have an idea of how many misreceived packets have been associated with the session. In order to implement the testbed, we leveraged the microservices-based approach by using Docker containers, and basically we are using the Docker Compose framework. I think that some of you might be familiar with it. Basically, this framework allows you to properly spawn a number of containers and to dynamically and quite easily define a configuration for an entire network that you can host on a single computer, on a single machine. For our tests, we used Ubuntu operating systems, and we spawned a number of different nodes, each hosting one of the components of the overall testbed I was describing. In particular, we leveraged an 8 Intel Core machine, so we had 8 CPUs, and by using the CPU set option of Docker Compose, we could allocate some of the CPUs to a specific component of the testbed. In particular here, we used 4 cores which were allocated to Janus and 3 cores to Jattack. One single core was dedicated to the controller, which is much more lightweight when compared to the others. We present some figures in the paper related to the video room plugin. As you might know, Janus is capable of implementing a number of different scenarios. The video room plugin is the one associated if you want to video conferencing, for example. So you may have some publishers which are streaming video and audio data, and such streams are shared among a number of participants. Some other participants might be just passive, so they just attach to the conference and they want to receive the streams, but they're not injecting their own contribution. And in fact, in the test that we describe, we have 10 publishers and 90 subscribers. So figure out a conference with 100 participants, 10 of which are the most active ones. But if you have 100 participants in such a scenario, this means that you have to manage a total number of 1,000 peer connections, because for each and every new participant, you need to create 10 peer connections in order to allow such a participant to receive all of the feeds. Please remember that this behavior is associated with the selective forwarding unit and not an MCU, which is a different thing. So let's come to the performance figures. This is CPU. As you can see here, we were monitoring both Jattack and Janus. The blue line is related to Jattack, the red line is related to Janus. And in the depicted scenario, we have CPU levels which arrive at values which are between 200 and 250%. Just to be clear, please keep in mind that since we had 4 cores allocated to Janus and 3 cores allocated to Jattack, we might arrive at respectively 400% and 300% before reaching saturation. As far as memory is concerned, actually we already knew that, but we had the confirmation. Both Jattack and Janus have a very low memory footprint, so I would say that memory is not an issue for our components. The operations that we carry out are much more CPU intensive than memory intensive. This is the estimation of the quality of experience, which, as I was telling you, has been derived by properly gathering information through the getStats command that is issued by the controller to the Jattack instances, and which monitors the number of not acknowledgement packets, the NACs, associated with WebRTC sessions. As you can see, everything, let's say, proceeds quite smoothly until we reach a threshold of around 800 participants, 800 users, What happens afterwards is that we have a steep increase in the number of NACs that are generated, which means that the quality of the streams is becoming worse. We actually were happy about the fact that we were able to spot out this weird behavior, because as you see, none of the CPUs was really under pressure, let's say. The conditions were quite okay, so we were not expecting in the beginning such a behavior, and we were investigating why this happened. At the time of the writing of the camera-ready version of the paper, our clue was that there was an inability inside our media server related to the routing of let's say, so significant number of packets for delivery to the different recipients that we are managing. And we tried to spot this out and to work on this in order to fine-tune our implementation. Actually, what I have to say is that during the last few weeks, we have kept on working on the analysis, and what we found out for this specific situation is that in this case, it was not, let's say, our fault. So our code was quite okay, the router was performing well. The issue that we were able to identify was indeed related to one of the most important libraries that we're leveraging inside our code, which is the libnice library, which many people use all around the world, which is an open source implementation, a very good one, by the way, of the ICE protocol stack. But what it does actually is that it uses a lock, a global lock, when it comes to delivering packets. And actually, this is okay if you're using libnice inside the client, because you're not going to manage a very high number of agents at a time. But if you are leveraging such a library in a server, this becomes a real issue that you have to face. And indeed, we opened let's say, discussion on the official mailing list related to the development of the libnice framework, and we are currently interacting with the authors of the library in order to fix this issue. We were able, by the way, to, let's say, find a workaround on our own by simply removing the global lock and associating the lock to the, let's say, on a per agent basis, which really allowed us to speed up a lot performance. Actually, we completely removed the performance bottleneck associated to ICE, but this is a, let's say, a dirty hack that we did, because we're not 100% sure that we're going to avoid race conditions and the like. That's why we did not contribute, at least as of yet, we have not contributed our modifications to the open source community. What, sorry? Yeah, actually with our modification we completely removed the bottleneck associated with NACs, and we were able to reach the threshold associated with saturation of the CPU. See, let's say that now we are sure that we're not depending on libnice for the performance, and now we have to look into our own code. By the way, let's say, before concluding, I would like to make a dangerous thing. I would like to show you some real-world stuff. So I have here let's say, very, very narrow-scoped version of the testbed. I just launched a number of containers on my laptop. You can see there we have actually Jattack, Janus, GStreamer, a controller, and an Nginx proxy, which is used in order to, let's say, act as an interface towards Janus. I can start a script which basically starts Janus. So if I go here, if you're familiar with the Janus interface, this is the demos page associated with Janus. I'm using, in this case, not the video room plugin, but the streaming plugin. There's a list of streams we can get connected to.
Discusses with his bosses and his colleagues the possibility
So basically, here I'm streaming something by using an RTP stream, which is generated by GStreamer, which goes to Janus, and then is, let's say, properly switched onto a WebRTC-enabled stream. And here I have one viewer. This is confirmed if you use the Janus admin API. Here I have one session, which is a WebRTC session. I have one handle, that is this one, and I have information about all the things that have happened during the negotiation and setup of the session. If we go here, we have the WebRTC internals from Google. And for example, you can see here the information related to the stream that I'm managing, okay? So basically, this is just basic usage of Janus. And if you already played a bit with it, you're familiar with it. Now, what I can try and do is connect to the controller, which is this one. And I can start the controller. Just give me a second. Okay. I have a scenario that is associated with the streaming. So now the controller is ready. And now I can go and play with the Jattack instances. So I can attach to Jattack and start the hammer, let's say. So now what I'm doing is I'm generating every 1 second a new WebRTC session by properly emulating the behavior of a browser. So what happens here, if I go here, is that you will see that the sessions are now 2. I have this one, and here I have an increasing number of handles, actually 1 per second, which means that now Janus is going to manage all those WebRTC sessions. And I will arrive at 150 sessions, which are all streaming sessions. The thing that happens here is that you can also, let's say, properly manage the quality of experience that is perceived by the users by using this real instance. So now I'm managing one real WebRTC session through Chrome, and I'm adding an increasing number of new sessions which are completely, totally equal to this one, but with no user interface, no representation inside the browser, and so on and so forth. But from the Janus perspective, this is exactly the same thing. So if I go to one of these handles, for these handles, you will see that I'm really receiving packets. So these are real passive users of a Janus-enabled streaming session. If you look at the internals, you will notice that as soon as the number of sessions becomes consistent, on my machine here, which has just 2 cores, and I have dedicated 1 core to Janus and the other one to Jattack, I will reach a bottleneck actually, and in a while the quality of this video will be worse than it is now. We can perhaps change. Okay, if you see, the video becomes has glitches, the audio becomes crappy.
You can exchange brief text messages. In addition, thanks to the telephone bridge, you can attend the meeting wherever you are.
Now I am at 150, which is here a threshold. I'm not going above this threshold because otherwise I will stuck my computer. Okay? And so basically here you can see that the stream has become much worse than it was before, and you can have an idea of what is the optimal deployment for a single instance of your Janus server. Now we'll stop everything here. I would just like, before drawing the conclusions, I would just like to draw your attention to a very simple consideration. I have generated on my laptop 151 WebRTC sessions. If you try and do this with, let's say, Chrome instances, browser instances on a single laptop, you will never reach this number of clients. Even if you use frameworks like Selenium, which allows you to properly automate the testing on the client side, and you want to properly stress test the backend server. I can tell you this because we have been using these frameworks quite extensively for our campaigns, and if you have to buy machines on AWS in order to perform a scalability assessment, you have to buy at least one order of magnitude more machines that we are allowed now to do with this Jattack tool. So basically, the conclusions are that the tool works as expected. The future work concerns both the, let's say, application of this kind of paradigm to the testing of other media servers and components, which is something, by the way, that we are already doing, but I'm not presenting any results here because I do not want to talk about other people's stuff. But believe me, it's really interesting. If you want to draw comparisons, this is something that is really useful. And one other thing that we think might be done is keep on using Jattack not just for stress testing WebRTC servers, but to, let's say, use it as a very flexible client-side WebRTC gateway, which means that it can be used in order to properly interact with any kind of WebRTC-enabled server, because basically what it allows you to do is to have available a complete and fully fledged WebRTC stack that you can use both on the client and on the server side. From our perspective, obviously, this is the same exact stack that we are using inside Janus, but the core, has been easily reused in order to implement a client behavior. So that's it, basically. If you have any questions, I'll be glad to take them. Otherwise, I'm done. Thank you. Please.
So this was to test. This is designed primarily to test the media, the media connections. Did you also do anything to test the signaling for?
Yes, this is a good question. Actually, we already have a number of tools available for signaling stress testing, which is interesting on one side, but is, let's say, it's not going to become the bottleneck in any case when you are going to deliver real media. So for the signaling stressing, you can use a number of tools. I'm not mentioning any of them right now, but you can start by, let's say, using your own made protocols based on JavaScript, JSON, and RESTful approaches, or more advanced ones based on WebSockets or RabbitMQ asynchronous notifications. All of these work. The real issue becomes when you have to deploy in the cloud or in the net a number of media server instances, and you are not aware of the real figures that are associated with the performance of such components. Actually, we were motivated to carry out this work mainly by, let's say, our customers, so people who are using, companies who are using Janus and who keep on asking, what are the figures associated with this component? What should I do if I want to deploy them in the cloud, if I have an envisaged number of clients that goes from this number up to this number? We were not able to provide them with the right answer because we had never been capable of properly stress testing even a single instance of our server. And now we are much more familiar with those figures. And the other important thing was that we were able to spot out small bugs and issues in our code and to fine-tune the implementation, which is something very, very important because debugging a WebRTC session is really something that drives you nuts.
So you're using GStreamer as to send the video streams, and you built your own receiver essentially that's receiving them?
If you need the Jattack instances to inject media, GStreamer can also be used in order to send RTP data to Jattack instances, which then send WebRTC data to the media server on the other side. In this specific case, the one that I was showing, I did not need to send media directly to Jattack just because I was simulating the streaming scenario. So Jattack were passive users. And so the only one who needed to receive the injection of the stream was Janus, because it was acting as the selective forwarding unit for everybody. But if you go, that's why I was showing the simple scenario here. If you go to the video conferencing scenario, you need media sources to be attached both to Jattack and potentially to the backend server. But GStreamer is just one of the potential sources. You can use whatever you want.
Yeah, because I guess my next question was, is that a sufficient, is the NAC and media engine behavior enough to simulate what a Chrome or Firefox browser would do? Is it a realistic test?
Yeah, that's
Or
a
is it
great
just
question. Yeah, actually, you cannot rely just on NACs if you want to have a quality of experience estimation. QoE is something that goes really beyond that. It's much more complicated. That's why I was showing the real thing by saying you can look, you can watch the movie, listen to the audio, and you can tell me in a, let's say, MOS similar way when you're satisfied and when you're not satisfied. We're working actually quite hard on ways to automate an estimation of the real perceived quality of the streams that you're receiving, which goes far beyond the analysis of the NACs. This is really a coarse-grained approach. But, I mean, it already allowed us to spot out something that was weird, because if I receive NACs and the CPU is okay and I have no networking bottlenecks and memory is okay, there's something weird that's going on. And it must be a lock, in fact.
Simon, was this SRTP streams or RTP streams?
Everything inside WebRTC is
SRTP.
secure RTP on top of the TLS.
Right, so this was...
The plain thing was just between the GStreamer and the SFU, which was plain RTP.
So CPU percentage and everything includes the decryption and everything?
Yeah, sure. It's completely 100% WebRTC. And in fact, the bottleneck there was ICE, which, as you know, is mandatory inside any WebRTC implementation. And we use trickling, by the way. So as soon as you have a candidate available, you just send it out. But that's not CPU, that's latency. Yeah, it is latency intensive, this part. And basically, we were skipping all the, let's say, latency-related issues associated with potential bottlenecks inside the network, which, as I was telling yesterday during one of my comments to one of the presentations, becomes the real bottleneck if you, for example, make deployments in the cloud of this stuff. Because there's no way, for example, as far as I know, to the best of my knowledge, there's no way at all to ask Amazon to provide you with guaranteed bandwidth if you want to talk about bandwidth that goes from your side to the cloud, not intra-cloud bandwidth. So you can buy M4 large instances, they're okay, but the networking part is not, at least it's not officially negotiated through an SLA with Amazon. And this holds true for Azure and for the others.
Hey, just a quick extra question. So that tool is certainly great. Actually, I love your presentation and the initiative. Great tool to
Thanks.
potentially test different types of media servers. I was curious, did you ever try to apply it also on some turn servers? Because the same way it can be a great tool to check the capabilities of turn servers. I mean, they do much less of heavy lifting compared to real media conferences, but they have
That's-
bottlenecks.
that's
and
a-
it would be interesting. So did you
Yeah.
do any tests?
We're doing exactly this. I
Yeah.
have no figures as of now, as of today, but as you can imagine, turn servers, what are they? They're media servers deployed in the open internet, and we're relying on them. Everybody's relying on them. If you take Slack, for example, they use turn server for each and every connection that they do. And so these are going to become the real bottlenecks if you want to make a real-world deployment. And we're working exactly on that.
Okay, no, I mean, did you try that tool on some existing open source turn server or something? I mean, you can share that with me after the presentation. if you
No,
want
sure.
to.
No problem at all. We're stress testing open source implementations of the turn servers, the co-turn implementation that everybody uses. What is not open source and which, let's say, is not quite in line with our typical philosophy is Jattack is not open source. Janus is 100% open source. All the things that we do are open source, but Jattack has not been open sourced as of yet. And there are a number of reasons behind this, one of which
do you
is...
plan to open source it eventually or no?
I have no clear answer now. We were discussing this internally because, first of all, we're making some business out of this. And second, I think that Jattack might become a dangerous tool in the hands of an attacker for denial of service attacks. So it must be used with some caution, I would say. And we're thinking of licensing, actually, it for companies that are interested in using it. So it's something different with respect to what we are used to do. Thank you.